All right, continuing from the previous episode where we just started talking about how to think about type 2 partial fractions, repeated linear factors. This is going to be a continuation video and episode on the same topic. Now let's understand. Now let's say in the last episode we have learned how to identify without getting confused whether the problem belongs to type 1 or type 2 or type 3. Now let's say you are expert in that and you're very proficient in identifying the problems, and there are two problems given to you. These are the same two examples I've taken in the last episode also, if you remember, on explaining the concept. So you can read this in terms of continuation. So let's say we've got two examples, and our objective is to decompose or solve both of these rational expressions into partial fractions. That's our objective. And there is a reason why I chose these two examples in specific, because there are certain nuances which I wanted to explain using these two examples because it will be clear. And you'll see that in this part and the next two parts where I'll be taking and solving these problems, okay? Like we did in the first part for type 1, if you remember, partial fraction is all about taking a rational expression like this and moving into partial fraction. But we did kind of the opposite of that. First, we understood what will happen when we move from a partial fraction into a rational expression, what are the steps involved, and we kind of applied those learnings on those steps to kind of solidify and cement our understanding on type 1. So we'll do the same exact opposite just for the fun, but it will give us a lot of insights on why we do certain things with certain types and what is the difference between type 1 and type 2 and how do we think about that, okay? So let's get started. So let's take the example first, example 1 over here. And what we will do is, we will do the opposite of that. We will not start from the rational expression, which is what we will do eventually for solving partial fractions. But just for the sake of understanding and getting some intuition on this example, we'll do the opposite of that. We'll start with the answer first. This is the answer I'm telling you up front, whichever is in the green color. So once you decompose this rational expression, will be your answer. So let's assume for a minute that we are not doing partial fractions. We have been given partial fractions. And our objective is to convert this into a rational function, which is in the blue color on the right hand side, if that's the objective. If that was our objective, what we would have done and how we would have gone about that. We would have done a simple multiplication or taking LCM and cross multiplying, and we would have gone on simplifying the expression as long as we want till we cannot simplify or we cannot do anything further with that. And those are the steps here which are very self-explanatory, where we take the LCM on the denominator, we cross multiply the terms over here, then we open up both these brackets, we expand it. Over here, if you see this x plus 2 the whole square is expanded, and then we kind of bring in the like terms for 4x and 4x and everything together. And finally what we get is x square with all the cancellations and knockoff and everything. What remains finally is x square divided by x plus 1 and x plus 2 the whole square, which is what the right hand side is, okay? And this is what would have been the right hand side or the rational expression. So we are not done with this, okay? Now let's observe what happened between these switches, right? What happened when we started off or converting this expression from one thing to another, whether we moved from left hand side to right hand side or right hand side to left hand side, does not matter. But let's understand, now we know that what is the partial fraction and what is the corresponding rational expression, or vice versa. What is the rational expression and what is the partial fraction? Let's understand what happened here and what are the typical patterns that we are seeing in solving this kind of problems, okay? Now, because we already know that these are repeated linear factors, we know that. So let's see what's so special about this, okay? So what did we observe here? The first thing is, what did we observe here? This was your rational expression, okay, RE, and this was your partial fraction. Although we started from this and ended, don't worry about that now. Now we know what is the pair doing, what is the pair of rational expression and partial fraction look like. We know that. So this is our rational expression and this is your partial fraction. So what does it look like? So if I substitute this thing that I have highlighted in yellow as a constant, A and C, I've taken C, not B, notice that, and there's a reason for that. So if I substitute that, looks like when I decompose this partial fraction, because I've done it in the reverse way, now I know the answer. So if I do a reverse engineering, I know that if I decompose this given rational expression into partial fraction, it's going to look like something of this sort. And what do we see here? we see the same terms as the denominator separated out, and there are two constants in the numerator, just constants. And again, in that fashion or in that regard, this is no different than type 1 except for a couple of nuances, and we will see once we take example 2. So this looks the same thing because we have split all the denominator is the same, but it's a split per factor, and we have taken two constants. Okay, so remember this for now. Example 1 has two constants A and C, and there is a reason I missed B. We'll come to that. So we saw that. No big deal so far. It looks like, okay, what's the big deal? We are not getting that, or we are not yet seeing it. Okay. Now let's take our second example, which is what we have been referring to over here, which is what we have done in here also. Let's take this example. Okay, almost similar example. Okay, and I'm not solved it in detail, but let's say if I were to do the same opposite, where I start with the partial fraction and I end with the rational expression. This is the expression that was given in this problem over here. If you see this one, example 2. So on the right hand side, so if I do the opposite, where I start on the left side with the partial fraction and right side, now we have the duo of rational expression and partial fraction. We have the pair now. Doesn't matter what is coming from what, but let's hold on that we have a pair of partial fraction and the rational expression which are matching to each other. So what do we observe in this case? Because both these examples, example 1 and example 2, belong to the same type 2 repeated linear factor, right? We know that we have done in that previous episode, and we can see that that's very evident. But what is so obvious, or what are the nuances that separates these two examples, right? So what do we see here? What do we observe in this case? So this is like your rational expression over here, and this is your, all the things in green are kind of the corresponding partial fraction. So what do we see here? For the same expression, what we are seeing here is this particular partial fraction has got three constants. So we have a constant here, we have a constant here, and we have a constant here. And if I substitute each of these constants in the numerator by terms or by variables a, b, c, or constant variables a, b, c, then it looks like this has got three constants in this case. Okay, and whereas the above case has got only two constants. So now that's kind of the nuance, like, hey, what just happened? Like one expression which is the same thing, the nature of the problem is same, both appear to be type 2 repeating linear factors, but one of them, when we split or decompose them into a partial fraction, one of them just has got two constants. And what are those constants? The first linear term is simple, that's same in this a upon x plus 1 is same, but in this case the middle term is missing, and if it directly shifts to a constant divided by the second term, which as it is x plus 2 the whole square, right? That's what we see here. Okay, which kind of looks like it's a type 1 problem. Looks like, it's not. Okay, type 1 non-repeating linear factors. And over here, if you see, the first and the third term are same here. If you see, the first and the third term are same here. This is same and this is same. And the additional term that we are getting here is a constant b, because we know that, okay, this is the expansion, or this is like the simplification of that. We know that upfront. So there is the additional term that is b in the numerator, constant. And in the denominator, what does it say? Whatever is the repeating factor, without the repetition, just the linear part, right? Just using it once, not repetition. The second term represents that as if this both were a type 1 problem where you would have just had x minus 1 and x plus 1. This is how it would look like. So again, let me repeat it if I had gone too fast. The middle term looks like there is a constant, and in the denominator, what is happening is it is just giving me a middle term which is a part of the repeated term, right? In this case, we take x plus 1 the whole square. Whatever is there given in the equation, it's expanded, it's taken to the whole square. And this I will tell you how did we get from x plus 1 into x square minus 1 and this part, because we expanded this using a square minus b square. We have done in the previous episode. Nevertheless, I'll be solving that problem. But once we solve that, this is the answer. So the first and last term are same here because it shows the repeated term to the actual power. Whatever is actual power, if it's raised to 2, we have seen 2. But the middle term is one of the factors of the factor is still the same, which is the repeated one. but it's not raised to 2, it's just linear in nature, where it is just the whole thing is raised to just 1, it's not done. That's the extra term that is coming in, right? And the question is how and why. How would we know? Because you will be given these 2 examples, right? Just these 2 examples like this over here. Hey, decompose this into partial fractions or solve this into partial fractions. You know on the face of it, it's type 2 repeated linear factors. But how would you know that the opening step, the first step, that when you simplify and bring in the constants A, B, C, whether you need to bring in 2 constants or you need to bring in 3 constants? How would you know that? And that's your $1 million question over here, right? So let's try to address the question and the answer. So the question is, how would I know in advance, given a rational expression, okay, that is the example 1 and example 2 I saw. If that's what given to us, how would I know in advance if the corresponding partial fraction for this particular solutions, the partial fraction for each of these example, either would have a 2 constants or 3 constants or more based on the example that we saw, right? Example 1 had 2 constants, example 2 had 3 constants. How do I know that? That's the question, right? Because I need to know that, although I know it's type 2, but how do I simplify the first step? How do I do my opening step based on the number of constants that I need to bring in? That's your $1 million question. And the answer is very simple, but I want to go slow so that you're focusing on that, right? So since you do not know upfront, or you won't know upfront whether it's 2 or 3 constants, what you do is you factorize. We know that both the examples we need to factorize first, right? We need to simplify that. That's what we have seen, right? In the previous episode, if you see, if I scroll a bit above, which is where I'm going to the previous episode, the continuation of that, I'm taking this example 2 and I'm factorizing it, right? And rearranging that using the a square minus b square, and this is what I get if you see here. And what do I see here? After factorization, I see 3 terms. That's what we have seen here also. The post factorization, the denominator has 3 linear factors. So there are 3 linear factors. And similarly over here also, once we simplify this, there are 3 linear factors in the denominator. That's what we see here also, right? So in both the cases, after we factorize into all the linear factors, because it's a linear repeated factors, the denominator has to be linear. So just see how many factors are there in the denominator after factorization. After the factorization, see how many linear factors are there. And you just assume as many constants as the number of linear factors. In both these examples, after factorization, we saw that we had 3 factors, 3 linear factors. We saw that, right? So we will assume that for both these examples, there are going to be 3 constants, and that's how we'll have our opening step. And that's what we'll do that. We'll not worry about whether it has got 3 or less. We'll not worry about that. If we know that post factorization, the number of linear factors are 3, which includes repeated and non-repeated, we will assume that there are going to be 3 constants for each of the terms, like this A and B and C, and not worry about whether it might have 2 or not. We'll not worry about that. We'll just assume to start with there are going to be as many as constants, in this case 3, as the number of linear factors post factorization, okay? That's what we are going to do. And what's going to happen is, if your assumption is wrong, in this case, in the example 2, your assumption is going to be correct, because it's indeed 3 factors. If you saw it here, when we saw it here, it's indeed 3 factors and 3 constants. So assumption is going to come true. But in the example 1, your assumption is going to be not true, because you're going to miss the B. That's why I missed the B and kept C intentionally, so that you can understand. You're going to miss the B, which is okay, because your assumption could be wrong of 3 constants, but that constant will have a value of 0, which you can eliminate later, but at least you can solve the problem. That's what it means. So assume that, and if the value becomes 0, don't worry about that, okay? Now another important thing of why you need to have this, why we should have these 3 terms, right? So if you think about that, okay, let me see what is the best way to explain that, okay? So the best way to explain that is, okay, so in this case, we know that once we solve the partial fraction, we are going to take the common denominator, right? So let me just create some room here. Hold on, let me clean up and let me see if I can create some room for you. So we know that what we're going to do is, after we start with the problem, the first thing is, once we simplify that, we are going to check out for the common denominators, okay? So if you see here, this denominator is always going to be common, whether it's type 1, type 2 or type 3. The denominator is always going to be common. But The denominator is nothing but once you cross multiply these terms, that's what we saw here, right? When we saw the previous example, we cross multiplied this when we saw this example to just get the intuition. Once we cross multiply that, when we take the LCM, we will not know what is whatever is the repeated factor, whether it's appearing once or twice, because the LCM is going to be the same, because the denominator will still give you the same. For example, in this case, once you take the LCM of that, you have this x minus 1, you have this x minus 1. Once you expand this term, right, this term will be 3x plus 2 x plus 1, which is the first term, and this term will get expanded using a square minus b square, so we will have x plus 1 and x minus 1. Okay, so this is the second term which is expanded, this particular term. So the first term, okay, it's there after you taking the LCM, but in the second term, when you take the LCM, whether you have this term or you don't have this term, you still get the same LCM, x plus 1 and x minus 1, which is x square. Once you combine these two terms, x plus 1 the whole square. I hope it's not confusing, right? So once you take the LCM to make sure the denominator is common, you will not know if this term was there or not there, because even if this term is there, the LCM is after the LCM the denominator is going to be the same. And even if the term is not there, in this case, even if you take the denominator, is still the same, right? So based on just taking the LCM to get the common denominator, we will not know to start with whether there was a middle term existing for the repeated factor without the repeated part of it, was existing or not existing. We will not know that, because both the cases could be true. In this case, the middle term is not existing. Still, after the LCM, the denominator is still the same. So there's no difference. You have x plus 1 and you have x plus 1 here, and you have x plus 2 the whole square, you have it. So once you cross multiply, the denominator looks the same here when we did the cross multiplication, right? Whereas in example 2, there was a middle term, and still the LCM for the denominator, once you do the cross multiplication for the rational and the partial fraction, the denominator ends to be same, right? So based on that, we will not know, because we know that we are going to do LCM and the common denominator. But just based on that, we will not know that the problem initially to start with, did it have the middle term or did it not have the middle term? And hence you assume that there was a middle term, which was nothing but one of the factors which was repetitive, but you don't take the repeated power of that and you keep it simple. And then you solve to see if it actually existed, then this value is going to have some non-zero value, like we saw in example 2. And if it did not exist, then it's going to be 0, and then you can eliminate that. And that's the reason you need to figure that out. So the last point, from an LCM standpoint, denominator, an extra middle constant linear term is always possible for the repeated factor. We will not know that upfront. So that was kind of the explanation. This part is slightly tricky. So in case you guys don't understand, post comments, I'll try to explain that. But nevertheless, you get the drift of overall this thing, right? So what do we do? For the example 1, instead of having this A and C and doing this term, we will do this, okay? So meaning instead of taking two constants like this, missing the B part, we will take 3 constant. We'll assume that the 3 constant exist to start with, and once we solve, the answer of B will become 0. We'll see that. So the way we'll do that is, this is a typo here. Let me just remove here. Okay. This part is not existing. Sorry, this is not 2. So what we'll do is, the first constant will have the denominator A into x plus 1, and we know that the repeated will stay as it is. We have the last term C divided by x plus 2 the whole square. But we know that there could be possibly another term with the same factor but without the repeating part of that. So I've removed this. I'll correct in my notes. So B upon just x plus 2. We will not take this power into consideration, because it could exist, because when we solve for the LCM, it still gives the same LCM when we solve for that, right? And then if your assumption is going to be wrong, which in this case is going to be wrong, your answer will be B is equal to 0, and this will automatically go, and all you'll end up with is back to this or this, right? And that's how you solve the problem. So those are the nuances of what separates you on how to solve type 2 from type 1, and within type 2, how to think about the number of constants. So it's very simple. After you factorize it, and all the factors are linear, so if the number of factors are 3 linear factors, assume that there are going to be 3 constants, and like that, and then you solve that, and then you'll be fine. So in the next episode, we'll solve this actual problem to apply what we have learned, and then we'll see how the real time it works. Thank you.